information about the nanotechnology and how this nanotechnology can help us to solve the problem of water and water related other issues like water reuse, water recycle, and water preservation. So nanotechnology has a big effect or big application in this water treatment sector. And in this seminar, I would like to give you a brief account of this too. So why we are concerned about water? Because we all know that water is everywhere. So almost 75% of the earth's surface it is filled with water. Then why we are concerned about the water? That is mainly we are concerned about the fresh water or the water that we can consume. And if we just look, what is the percentage of the fresh water available to us globally? That is less than 1% of the frozen water that is already have on the earth's surface. So that amount is obviously very, very low. And we are concerned about the water and water treatment because we want more and more fresh water. So the fresh water availability is mainly the requirement or in the present days, and the water scarcity that we are talking about all through the globally we are concerned about the scarcity of the water, that is mainly the fresh water. Fresh water or the water having potable water and the drinking water. So this is just a picture. There is some statistical and a presentation about the water scarcity scenario in this world in present days. And as per the Director of National Intelligence, this is the picture of the global water scenario, where these red zones or these dark shaded portions, they are mainly mentioning the extremely more stressed region and exceptionally more stressed region. Obviously, India, some part is also in this region. So this is the water stress level that is already reported by the Director of the National Intelligence. Now, those water stress, how this water stress affecting us? This water stress having a big impact on our health also. With this statistical figure is showing us how the death is related for with the unsafe water consumption. And obviously you can see for the India the scenario is very very critical. About as per the WHO, the about 500 to 1050 people per million they are dying due to consumption of the unsafe water. So the situation for the India is also very critical. Now this critical situation, why it's arising, those are mostly for the anthropogenic reasons. That is, we are mainly responsible for all these water crises. We are the human beings are mainly responsible for all this. How? Because we are discharging the water. Okay, discharging the water, surface water discharge, that is mainly causing the problem of the plant growth, that is damaging the aquatic flora and fauna, and ecological balance is totally disturbed in this way. Now, people, some industries, they are discharging in the seawater. What is happening there? The sea life or the aquatic life that is getting damaged. Industries, they are also discharging on the land. What is the effect there? The groundwater getting contaminated with all of the contaminants. That is the industry they are discharging without treatment of the water. So all of these reasons for this contamination of the water, those are all anthropogenic and all are related to our misuse of the water and not treating the water before it's discharged to the environment. Some report is also there, that is the very recent report of IIT Bangalore, that is the microplastic, how it is affecting the corporate fishes life, aquatic life. So these are a microplastic is also an emerging pollutant. It is coming into the picture very rapid at a high pace. So we are all concerned about this of the micro emerging pollutants, and all those are for our misuse and for not treating the water before it's discharged. This is also a picture that is published in the Telegraph, that is in the Nazarkar drain along the Haryana and Delhi border. How the fishes they have been suffered due to this discharge of the industrial effluent without any treatment. So the situation is obviously very critical, and some of the studies that is reports are there, which is of the Niti Aayog, that they are telling that about 2 lakh people die every year due to the inadequate access of the safe water. And they are also telling that the 21 major cities of the India, they are just racing to reach the zero groundwater level very soon. And India ranks third from the last among the 122 countries in the water quality index, because the most of 70% of the water resources of India, they are contaminated. Now, since this situation is there, now Indian people are, India mostly, they are becoming dependent on the monsoon, the availability of the water, that is fresh water, the monsoon. But that also has become very problem because of the global effect, global warming effect and the climate change. And the fresh water availability for India is just trickling down very high at a very fast rate. So these are some of the reports that Niti Aayog they are developing. This is also the report from the Niti Aayog. They are just telling that as per this report, that demand and the just water supply, and it is observed that by 2030 about 744 million billion cube meters water is the it can be supplied, whereas the demand will be about 1,498 billion cubic meter. So the shortfall is about 50%. So that is obviously very alarming situation. And not only this demand and the requirement, but also availability is the matter there. If you can see this report, the availability of water, that is the fresh water, that is also becoming very, very low. That is also falling. Now, we are not only concerned about the demand or the water that we are supplying, but we also have to consider about the availability of the water. Now, this water availability we can control. Why? Because the water we can't just produce or we can just supply to anyone. What we can do to make this availability to increase, that is by the reuse of the water, recycle of the water, and preservation of our water bodies. So by this way, the availability of the water it can be increased, and if this availability is increased, then we can meet for the demand and its utilization. So for the Indian perspective, we should consider about to increase the availability of the water, increase of the availability of the water in terms of recycle, reuse, and preservation of the water body. And this is also a statistical analysis which is showing what is the drinking water challenge that India is facing. And in about 6 houses, among the 10 households, they are not treating the water. That means they are taking unsafe water. And 163 million people, they have no access even to the safe drinking water. Students' life and people life, they are also getting damaged because of the waterborne diseases. About 21% of the diseases reported in this country, which is related to this water. And also, two major threats are there, that is the contamination of the fluorine and the arsenic. About 66 million people in 20 states of the India, they are suffering from fluoride contaminated water, which is damaging not only the health of the people, also for the child that is skeletal defect, the dental problems are all associated with this fluoride contaminated water. And arsenic, you all know that is it is also very threatening. And arsenic contaminated water, that is the people who are taking the groundwater, they are mostly taking this arsenic contaminated water, which is also causing severe health problems. So these are the scenario for the water scarcity or water problems, which is now prevailing all over the world, not only all over the world, but also in the India, also in India. Now, since the situation is very grave, so the central government, they have already started a program, that is Jal Jeevan Mission in 2019. And in the Jal Jeevan Mission, the main theme or the main aim of this program, that is mainly to provide the good quality drinking water through taps to the every rural household by 2024. And in the Jal Jeevan Mission, just the report which has come, which is in our hand, that is, in Jal Jeevan Mission, we can prevent about 1.36 lakhs under 5 days per year by providing tap water free of microbiological contamination in every rural household. And the scenario is also there, that is the National Center for Disease Control. They are also reporting a remarkable improvement in the water quality and how it's improving the life of the people. In 2019, there was waterborne disease reported was 177 lakhs, which have been reduced remarkably in 2021 to 29 lakhs only. So this showing that how the water treatment and this availability of the good quality water to the to the human race is is important. So there lies the importance of water treatment. So water treatment, we have to consider about the water treatment. Now treatment in which respect? Treatment means what we are taking mainly drinking water, we are using drinking water and the potable water. Now in drinking water and potable water, the difference is mainly the presence of the microorganism. And where from this water is coming, the potable water, we are just taking this after treatment from the water body. It may be groundwater, it may be river water, or it may be some seawater. Now, seawater we are not discussing here, because in seawater normally there is lots of the ions, that is the salt is there, and in the salt, when it is highly saline water, seawater, only one option is there for the treatment, that is the reverse osmosis, that is a membrane separation process is there, that can only separate those ions or that is the salt from this water. Now, other waters, that is the sweet water resources, that means the river water or the lake water or the groundwater. Now, this water, they are contaminated. They are contaminated. Why? Because of these anthropogenic activities, mostly due to the disposed effluent, that is industrial effluent, which is coming into the picture, and every day they are discarded to this water bodies. They are contaminating those waters. So we need this water treatment because it cannot be generated. We can't generate water. Only we can preserve water, we can recycle water, we can reuse water, but we can generate water. So that's why the water treatment is very, very important research domain, research and development domain. And in this water treatment, our main objective is the toxin removal. So that it can be just comfortable for our consumption. And in terms of it may be potable water or it may be just drinking water. And for this water treatment, the conventional processes are like biological treatment processes there, the coagulation processes there. All those processes, they are associated with the production of the large footprint, and also they need final polishing stage. That is, polishing stage is very important because without the polishing stage, that is the third step treatment of the water, you cannot use this for drinking purposes. the polishing stage is very important in water. That is also a mandatory part of the water treatment. Now, why this nano concept is coming? The nano concept is coming just as a polishing, not only as a treatment process, but mainly as a polishing step to give you a good quality water or safe water to provide for the individual as well as for the industries. They can reuse also this water after this treatment with the nano technological advancement. So in this way, nano concept is coming and it is obviously developing in present days for water treatment purposes. So, and also to mention that in the G20 meet, which happened this year in Kashmir, the main vision was also there that groundwater resource reservation, that is sustainable development and management of groundwater resource of our country. So this also we discussed, we have heard about a lot of the sustainable developments which are based on this nanotechnology, how this groundwater can be preserved or this groundwater can be managed. So everybody know about the nano, probably you know have heard the term that is nano. So nano, the definition is there, the nanotechnology means it is dealing with the matter which is in dimension of roughly 1 to 100 nanometer. And since size is mainly the concern here, the size is a main factor here. This size reduction is helping to develop some unique properties or some unique nature or characteristics of this type of materials. And we are just want to use these unique features of the nanomaterial for the for solving the problem of this water. How this can be done? So, nanotechnology in water application is not only a single treatment stage. Nanotechnology, you can apply this, sorry, nanotechnology, you can apply this in every aspect. Like you can just detect what is there or sensing. That means nano-based, nanomaterial-based sensor is there just to give you the idea whether there is any toxin or any contaminants in the water or not. That is sensing and detection that can be done by the help of the nanotechnology by applying the some uh, special features or unique features of the nanomaterial. Then comes the treatment. Treatment means removal or remediation and of the toxins or the contaminants from the water. So, whenever the water is contaminated, that means that contaminated water you can treat with the help of the nanotechnology. That is again and role and also the preservation. Whenever the resource is getting contaminated, some treatment technology is there which will prevent the contamination of the resources also. As for example, in groundwater, if it is groundwater is becoming contaminated, which can we can just use some of the technological advancement there. Some we can add some material there, which will just prevent the contamination of the groundwater, and the groundwater aquifer will be preserved. So nanotechnology application is manifold and not only for the treatment, it will help us in sensing of the contaminants for the detection, the treatment, the remediation and for the preservation. The threefold applications are there for this nanomaterial, that is the opportunities of the nanomaterial, the size dependent properties of the nanomaterial we are utilizing. Size dependent properties means that I have already mentioned the importance of the nano. If the size is reduced, some special unique features that is now developed on this for these materials. What are the properties? Obviously, if the size is reduced, normally the specific surface area that is now increasing. Sometimes some magnetic properties are developed there. The localized surface plasma resonance is there. Quantum confinement properties have been developed. Some unique mechanical, electrical, and optical properties are developed there. So, size-dependent properties of the material, those we are using for we use for these uh, water treatment purposes. That means those are basically helping us to detect and to treat water, contaminated water. Then second stage is nano-enabled treatment. Nano-enabled treatment means the nanomaterial we should design. We should design some engineered nanomaterial as per this our requirement in which mode we want to use those nanomaterials. Those are the specific features those are developed. Now, using this combination of all these features, we have to prepare the engineered nanomaterial, or we have to tailor our nanomaterial of our requirement. And there lies the absorption process. We can prepare the nanoadsorbent. We can incorporate the nanomaterial in membrane separation process. We can use this for the photocatalyst. We can use this for the microbial control and obviously for the sensing purposes. So, using these properties, we are now nano-enabled treatment we can design. And after this nano-enabled treatment design, what we can do, the final stage is the design of the technology development. With the material, we have to develop some technologies so that it is becoming economically feasible, it is compact, modular, and obviously of high performance. So the nanotechnology, the application is first of all based on its properties. We are generating some unique properties by size reduction. After that, we are designing our nanomaterial of our choice based on our application. And using this, after this, we are just want to prepare we want to develop the technology for this water treatment, which will be economically feasible, modular, and compact. Because the large installations are there, but if you want in situ treatment, then how it can be done? Suppose you are going somewhere and that safe water is not available to you. What you will do? You will go to some plant. You have to buy some water there. We know that plastic bottle water is also there, which is also the problem in present days. That is the plastic. And in the coming video, we are just discussing, will discuss about the plastic pollution and how to control. So you should buy the plastic water bottles for your water when you are going somewhere. Then, if some devices with you, so that you can just fit it into your water bottle and you just collect the unsafe water and you can consume that after treatment. You are treating this by your own when you are traveling and you are taking the safe water, then it will be also environmentally friendly and also good for you. This There lies the importance of the nanomaterial. Nanomaterial can give you that opportunity that in situ or when you are on go or what moment you are there, you can just have the safe water. That is individual supply of safe water. That is the benefit or that is the boon of the nanomaterial based water treatment. So this chart is also the same of the previous one that I described. That large surface area, how it is helping us. The large surface area to volume ratio that is helping us for a superior absorbance design, which not only remove the heavy metal but also the radionuclides. Enhanced catalytic activity that will also help us in advanced oxidation process and also the reduction process. Antimicrobial activity that will help us to control the microbes or the pathogens, and some multifunctional activities are also there, that is antibiotic activities and also the catalytic activity assembled there. Self assembly of the surface that is also helping us to produce some nano pattern on the surface and controlling the bacterial adhesion or biofouling and the corrosion effect that is reduced by the self-assembly properties of this nanomaterial. High conductivity of this nanomaterial, they will help in the energy efficient desalination process that is also called electrosorption process, and fluorescence properties that is developed in the nanomaterial that will help mainly to sense the pathogens or the contaminants in the water. Now, based on these applications or the availability of the nanomaterial, the nanomaterial has been classified broadly as nanoabsorbent, nanomembranes, magnetic nanoparticle, nanocatalyst, and nanosensor. So these are the broad-based classification of the nanomaterial. And I just want to give you a brief about the nanomaterials, how they are helping us, how they can help in the water treatment in terms of reuse, recycle, and the preservation. So first one is the nanosorbent or nanoabsorbent. So nanosorbent, in this category, we have carbon nanotube, nanoscale metal oxide, and polymeric nanoabsorbent, or these are sometimes called the dendrimers. In nanomembrane, the nanomembranes means membrane modified with the nanoparticle or nanofiltration membrane, nanofibril membrane, self-assembling membrane, and obviously an aquaporin based membrane, which is a biomimetic membrane. Magnetic nanoparticle, in the magnetic nanoparticle, we have magnetite and magnemite. Those also, the zero valent iron is also there in the magnetic nanoparticle, and that is also in the category, but it is not mentioned here. I'm coming to that later. And in nanocatalyst, we have lots of semiconductor nanocatalyst materials which generally help us for the uh, remediation or for the degradation of the persistent organic chemicals, which are normally causing high BOD load to the effluent system. Some fullerene derivatives are also there, which can be used as a nanocatalyst. And finally, the nanosensor, that is the quantum dot is there, graphene-based quantum dot is coming into the picture as a sensing material. And di-doped silica nanoparticle is also there. Carbon nanotube, sometimes it is also used as a nanosensor. And obviously, the magnetic nanoparticle is also there as a nanosensor. Now, what the nanosorbent? Nanosorbent, nanosorbent means it is having very high absorption capacity. Because since it is a nano size, its surface area to volume ratio that is very high, and they are very good absorbent. But whether this only single nanometer is an absorbent or it can be modified? No, the answer is not like that. The single nanomaterial can be used as an absorbent as well as modified also. So first vendor of nanomaterial that is solvent, that is the well known the carbon nanotube. Carbon nanotube is what is the carbon nanotube? It is the graphene sheet. Graphene or a graphite sheet. The single-walled carbon nanotube and multi-walled carbon nanotube, these two are normally used in present days for these water treatment purposes. And the single one carbon nanotube, you can see what is there. It is one atom thick layer of the graphite, or which is called graphene, in a seamless cylinder. And for the multi-walled type, we can consider about the two different designs. Either there is a Russian roll model may be there. That means the sheets of the graphite, they are arranged in a concentric cylinders, or the parchment model is there. That means it is single sheet of graphite. It is rolled many times so that it is forming a tubular-like structure, and it is also resembling like a rolled newspaper. So these two are the nanomaterials which are used for the good for mainly for the absorption as an absorbent for different type of the contaminants. Now, what is the basic features of this? Why we are using this as a adsorbent? Adsorbent of what materials, and why these are adsorbent? This is basically for the unique features of this carbon nanotube. That is, normally in carbon nanotube, we have observed that all the carbons they are in sp2 hybridized state. So the pi electrons are available there. And the hydrophobic effect, pi-pi interaction and hydrogen bonding and sometimes covalent bonding, they, with the contaminants, they are making this carbon nanotube is a superior adsorbent. Either the nonpolar molecules, that is when the pi electron nonpolar, those are molecules which are having some pi electron cloud there. They can be absorbed by this carbon nanotube because of these pi-pi interactions. Sometimes the polar components, which are also polar, that means having this type of function, they are not going to just get associated or absorbed with the carbon CNT by this type of pi-pi interactions, but that is basically by the hydrogen bonding they can form, they can be associated. And also some electrostatic attraction is there, which will facilitate the absorption of the positively charged organic chemicals. And these organic chemicals, mostly those are dyes that can be absorbed by the carbon nanotube. But those are, we have to make them suitable for absorption. That means we need some tuning over there, and that is the pH change. We have to change the pH such that they become positively charged and they can be absorbed by the CNT, that is carbon nanotube. So these are the basic mechanisms by which, that is for the polar, for the non-polar, and the molecules, organic molecules which are non-polar, but it can be made charged by changing or tuning the pH of the solution, that can be absorbed by the CNT. Now the CNT, why it's so unique? Because when we are just concerned about the absorption process, then the first concept coming into the mind, that is the surface absorption. The surface absorption is there. The surface you need very high. But in case of CNT, not the surface area, but with this, there are there are another three positions which are available for the absorption. Where are they? Their external surface, the first one, then we have inner surface. In the inner surface, it can also get absorbed. Interstitial channels. Interstitial channels, that means two tubes are there, and in between these interstitial channels, there also the molecules get absorbed, and also the peripheral groove. In the peripheral groove portion, they can also be absorbed. So why CNT is a good absorbent? The carbon nanotube. This carbon nanotube is unique because of the availability of all these four positions for the absorption. So compared to a single nano material, this carbon nanotube is very, very unique because it is providing us a very high surface area for absorption, not only the surface area but other portions for this absorption. And some report is also there. The total CNT specific area is very high. It's about 100 to 300 meters square per gram, leading to high absorption capacity. So this unique property of the CNT is making it as a good absorbent. And some report is over there, that is how this not only simple CNT but CNT derivatives, they can be used for the heavy metal removal. Normal CNT, CNT derivatized with the OH group, introduction of the OH group, CONH group, CO minus group. And then this group, this way, when CNT is derivatized, then they can be used as a good absorbent for the heavy metal. So where to use this material? The groundwater. If the groundwater is contaminated by some heavy metals, then you can use the CNT-based system for removal of these heavy metals from the water, and you can have a safe water. So CNT based system or CNT based units you can prepare, or we can prepare for having the safe water which is free of metal, heavy metals. And also uh, not only for that, the only any type of organic molecules, they can also be get absorbed because of the presence of this functionalized group. They can also be removed by this CNT process. Now CNT based setup. And then in the next type of the nano adsorbent is the nanometal and nanometal oxides. So nanometal and nanometal oxides, they can also be used for a good adsorbent material. Nanometal oxides, why those are so important? Because they normally they can just how they can react. They can complex form the complexation, that is the formation of the some complex with the undesired component or the dissolved metals or the contaminants as a faster rate compared to the nano, uh, that is a CNT based material. So that's why these nanometal and nanometal oxides are also good absorbent material, and we can use this for nano-based water treatment technology. And these are some of the examples of the nano oxides which are used for the heavy metal removal. That is graphite, that is first one, or also it is called the rust, the smart rust. Normally it is termed as a smart rust now. Hematite, magnetite, magnemite, zinc oxide, cerium oxide, titanium oxide, and modified aluminum oxide. All those are nano oxides. They are very efficient absorbent with a good absorption capacity for the heavy metals and heavy metals. And this is also the picture, that is polymeric nanoadsorbent. Polymeric nanoadsorbent, it is the polymer modified nanomaterial. In the core, we are having some nanomaterial. The nanomaterial, it is basically magnetic nanomaterial, that is super paramagnetic iron oxide nanoparticle. So this nanomaterial, now it is modified with some polymers. And if it is now polymerized, it is modified with the polymer, then we are having this type of structure. That means lots of functional groups have been introduced surrounding this nanomaterial. Now, what is the function of these functional groups that we have introduced through the introducing by the polymerization? This functional group will help us to absorb the complex with the contaminants or the heavy metals and other toxins, and they will be they can be easily removed by then after the treatment has been done by the magnetic separation. Since the magnetic core is there, so whenever it is just added to some aquifer and after the treatment we want to separate this, we have to present there, we have to use a permanent magnet there. If the permanent magnet is there, then what will happen? It will attract this core. Now it will attract the core, and if the core is removed, along with this, all the contaminants which are getting attached with this functional group, they will be also removed. So aquifer water will remain intact, but we are just removed the contaminants. That is the beauty of the polymeric nanoabsorbent, which is based on the normally magnetic nanomaterials, normally magnetic nanomaterials. And this is also a picture where it is BSA immobilized. So BSA, it is a protein. BSA protein is there. Though its application for the water treatment is very low, but sometimes for protein also helps in emulsification. So if we want to add a protein for the emulsification process, and we by emulsification we want to trap some of the undesired material within the core, then this type of arrangement will help us to remove those contaminants from the water. So this is also the polymeric nanoadsorbent, or sometimes it is also called dendrimers. Now, apart from this nano adsorbent, that is we have already discussed about, that is the nano adsorbent, that is CNT, and the iron oxide and different oxides, and also the polymeric adsorbent or the dendrimers. Next part is the membrane, nano membrane. Now, nanomembrane, you know about the membrane, that is membrane really works for the, it is basically the sealing mechanism is there. Separation technique, it is a separation technique is there. And for the separation process, membrane-based separation process, membrane is very efficient, and we can separate on the, that is on the molecular level also. The contaminants can be removed from the effluent and from the toxic water. Uh, that is the toxins can be removed on the molecular basis by the membrane process. But the problem of the membrane process is that mainly the fouling. and less permeability. And where there we can use the concept of the nano to improvise the function of the membrane. So function of the membrane, that is the membrane separation process, can be improvised by incorporating the nanomaterials in the membrane. That is the objective of designing all the nano membranes basically. So what is happening there in the nanomembrane? So nanomembrane, in this first category, there is nanofiber membrane. Nanofiber membrane, it is produced by the electrospinning method, and nanofiber membrane is normally used in present days for the microplastic. Microplastic separation is very efficient, that is the nanofiber membrane. Its ability, you can see it is a highly efficient one to remove the micron-sized particles from the aqueous phase and at a high rejection rate without significant fouling. So fouling is very low there in nanofiber membrane as well as the micron-sized particles are removed. So that's why using this unique properties, this nanofiber membrane, it can be now used, it is now being used, or the research is going on this nanofiber membrane to remove the micropollutants from the sources, from the water. Microplastics, basically the microplastic from the source water. And in this case, in case of nanofiber membrane, not only the removal of the micron-sized particles, but we can also incorporate some of the functional nanomaterial there, other functional nanomaterials. Some other nanofunctional material means like some metal oxides like TiO2, we can incorporate there. And if this TiO2 is incorporated with the membrane, what will happen? It will not only separate, but it will also degrade in presence of the UV light. Because those TiO2, those are semiconductor or those are photocatalysts. That means nanofiber membrane, its design is not only for the separation, but also for the remediation or degradation or the mineralization of the contaminants. That means if our water is contaminated with a microplastic as well as with some pharmaceutical components like some antibiotics, and you want to remove them both, then what will be our approach? We should use nanofiber membrane where the during the preparation of which we are adding some TiO2 over there. So whenever the effluent is passing through the membrane, then what will happen? It will reject the microplastic as well as in presence of the UV light, it will act as a photocatalyst and will also cause degradation of the antibiotics. That is the persistent organic chemicals, those organic molecules which are there, they can also be remediated or they can be also mineralized or we can get the environmental friendly discharge over there. So there lies the beauty of the nanofiber membrane. So nanofiber membrane, the picture is like this. This is the same picture for the nanofiber membrane. Electrospun polylactic acid nanofibrous membrane is there, and with the interspace void, the voids are mainly using that is the causing of the separation, or it is the reason for the separation. And this is the technically how we can prepare this type of this membrane. The solution, casting solution is there and it is injected. Some electrospin means some potential difference we have to apply, and these materials, they are now rolled and they are now collected. And whenever this materials is used in case of some filter media, if the water, contaminated water is allowed to pass through, then we can have the pure water also, not only by the filtration process, but also by the presence of the nanomaterial which may, if they are present, they may just degrade those organic pollutants also. So this is the nanofiber membrane where the nanomaterial concept or nanomaterial nanotechnology actually plays a role. Then nanocomposite membrane, that is the membrane modification with the nanomaterial. The membrane can be modified with during the not only the nanofiber, that is the nanofiber membrane, but other polymeric membrane or even the ceramic membrane, they can be also modified with some nanomaterials. Nanomaterials, what is the reason that I have already mentioned that we want more permeation, that is better separation and less fouling because that is the main reason of the membrane problem of the associated with the membrane separation process. So nanocomposite membrane, here with the casting solution, we are adding different types of the nanomaterials, that is nano, uh, nanomaterials means the metal oxides like alumina, titanium, zeolite, CNT, even the nano silver we are adding. All of them having different functions over there. And during the casting process, in the casting dope, we are adding this material and after that we are casting the membrane. So what the properties enhancement is there if we are incorporating the nanomaterial? If this material TiO2 is incorporated, it will help us, it will act as a photocatalyst. That means it will help us to degrade the persistent organic chemicals in presence of the UV light. If zeolite is there, that means what will happen? It will help us little bit more absorption. So not only the separation, it will also help us in absorption. If if silver and CNT is there, it will help us. CNT will help us in absorption, and silver will help us in uh, uh, just providing the antimicrobial activity. And some photocatalytic nanomaterial like other material, bimetallic nanomaterials, or some other multiple oxide, metal oxide combination that can also be used. They can also be used as an adsorbent as well as a catalyst for degradation of those unwanted materials or the undesired materials. So in this way, incorporation of this material in the membrane, we can prepare the nanocomposite membrane for or the smart membrane or the advanced membrane for water treatment. Obviously, this addition of this type of molecule, they will increase the hydrophilicity of the membrane. If they will increase the hydrophilicity means it will improve the flask properties. And if the flask is improved or the permeation rate, if it is improved, then obviously we are getting more throughput or more better separation and more throughput. And antibacterial properties, that means we are just preventing the biofouling. Suppose some organic molecules we want to separate and those organic molecules are getting absorbed on the membrane surface. Then what will happen? With time, there will be formation of a biofilm. So if the biofilm is produced, then what will happen? It will generally degrade the it will lower the performance or the efficiency of the membrane as well as they will sometimes also cause damage, permanent damage of the membrane. So, in order to prevent the formation of those biofilms, we can incorporate some nanomaterials like silver nanomaterials, which will act as an antimicrobial agent. That means they will kill or they will inhibit the formation of the biofilm. So in this way, nanocomposite membrane or nano-modified membrane or the membrane or advanced membrane incorporating the nanomaterial can help the water treatment by membrane separation process. And this is this picture showing in the different ways by how this membrane can be modified. This nanocomposite membrane can be prepared. The first one concept was that incorporation of the nanomaterial within the membrane. That means within the thickness of the membrane, the nanomaterial is there. You have added the nanomaterial in the casting dope and you have casted the membrane. So normally the nanomaterials are within the membrane. That means it is along the thickness of the membrane. It is along the thickness of the membrane. It is distributed. So whenever the feed is coming from that side, if it is a feed side we are considering, and it is passing through the pores, they are coming in contact with the nanomaterial and what the function is there that is happening, and after that we are getting the pure water as a permeate from this part. Then after that the modification is that why we are distributing this on the in the bulk, why we are not considering this for coating, because if it is on the coating as the coating we are using, that means better contact of the contaminant with the nanomaterials. Here, the probability of contact with the nanomaterial is much less. But if it is coated on the membrane surface, then obviously the better contact is over there. So the second option is that surface coated membrane, where the nanomaterials are coated on the membrane surface. But there is a problem also. In this case, the coating, the life of the coating, that is questionable. How long we can use this coating? That is a problem. That means for single use, suppose it's okay. It is not going to be get it detached from the membrane surface. But after twice, two times use or thrice use or four time use, how long we can use this? So lifetime is the problem question is there. So surface coated membrane is not so preferred, but whenever the surface coated membrane is combined with the concept of the thin film coating membrane, then it has become more advantageous for this water treatment. So what is there? The first is the conventional type nanocomposite membrane, and after that we are forming a thin coating. Thin film coating is there. And this thin film coating is helping the removal of a separation of some of the contaminants. And after when they are passing through, they are also getting degraded or the mineralization is done. But when this combination is used, that is very much advantageous. That is, the film, thin film is there. After that, the coating. After that, again a thin film. So better contact as well as separation both can be achieved. And lifetime is not also a problem because of the presence of the thin film over there, which is not going to get damaged with further recycle or several times reuse. Another also option is there if the thin film want to minimize the cost also because we don't want to use two films, then a single film can also be done. In that case, the material will be trapped with the thin film. So in comparison to the surface coated membrane, this one is also advantageous. So this one is the best option for using the composite membrane, but this option is also there where thin film combination with the nanomaterial we can use, and also the conventional approaches are like this. So these are the several techniques or these are the several approaches for uh, modifying this membrane with the nanomaterial. And this is also the picture which is showing how this nanomaterial helping in controlling the or reducing the biofouling effect. This is a simple polyether sulfone membrane, PES membrane. It is a polymeric membrane. And in this case, it is first derivatized with that is sulfonation was done. And sulfonated PES membrane has been developed. After that, this sulfonation is done, silver we have to incorporate this silver nanoparticle because ultimately for the biofouling we have to incorporate the silver nanoparticle. That means we have to add silver over here. How it can be done? So sulfonation was first done, then we are adding the silver nitrate. So silver nitrate ions are there, and when the silver nitrate is coming, it is not going to just get attached with the sulfonate group, but we have to make it a nano silver. For this purpose, what is happening? What is done normally? We are adding trisodium citrate to reduce this. So silver particle, that is silver 0, now silver plus 1, that was present here, that is now converted to silver nanoparticle by this reduction process using the trisodium citrate. So now after the treatment of the trisodium citrate, the silver ions may have now converted to silver nanoparticle. So since the reaction is involved there, so it is finally going to attach with the sulfonated PES membrane. So if the silver coated membrane in such a way it can be used, obviously it will help in the that is formation of the biofilm, or it will reduce the effect of the biofilm formation by its antimicrobial properties, and the result have been shown that how the flask has been improved. This was for the untreated one when the silver nanoparticle was not there. with time it has been decreased. But if the nanomaterials, that is silver nanomaterials, is incorporated, how the flux has been improved. That is, more flux we are getting. Obviously, because it's preventing the formation of the biofouling, preventing the biofouling. That's why this flux has been improved. So in this way, nanomaterials can be incorporated in the membrane, or nanomaterials modified membrane can be prepared. Then the magnetic nanoparticle. Already we have just discussed, I have just mentioned about the magnetic nanoparticle in dendrimer, how it can be used. And also the same effect is also there for the magnetic nanoparticles, because we know this magnetism, how this magnetism, what is this nanomagnetic nanoparticle? Because magnet is there, we know the magnet. Now what is the magnetic nanoparticle? Because we know that magnetism, how it is developed. The magnetism is mainly, it is the collective interaction of the atomic magnetic dipole. And if we are going to reduce the size of the magnet, then a critical value will reach when the magnetic susceptibility will be, with that it is increased, has been increased. And if from the critical value further the size is reduced, they have now become the super paramagnetic nature. And this super paramagnetic nature means they are losing their permanent magnetic moment. But what is done? They have become responsive for the external magnetic field. That means they are not magnets, but they can be attracted by the magnet. So the beauty of the magnetic nanoparticle synthesis is that size reduction, so that from the magnetic material, the super paramagnetic material man can be prepared, and those super paramagnetic material will be used will be incorporated with the membrane, or with the dendrimers, or with any other adsorbents for the treatment of the water. So obviously the best choice for is that nanorust or iron oxide nanoparticle. Nanomagnetite and nanomagnetite, those are normally considered as this uh, magnetic super magnetic materials for this function. And using this material, what is the advantage over there? That is better separation. You are adding this adsorbent, but you can also remove the adsorbent at a very easy, with a very easy manner. That is, no filtration, no centrifugation, no other techniques. That is the long process you have to apply. You just using the adsorbent, and whenever you want to separate this, after its functioning is done, you add a permanent magnet there, you place a permanent magnet there, it will attract all those super paramagnetic materials, and they will be separated from the media. So that's why the magnetic nanomaterial, they are so important. And this magnetic material like dendrimer we can use, not only the dendrimers, we can use some other silica coatings. That silane can be used. So silane can be used, silica coating can be used, any that is any materials can be just coated on the magnetic core. The magnetic core is mainly basically the magnetic material, and over this we are coating the different type of materials, and we are using this for the contaminants removal. We are adding this to the contaminated effluent, and whenever they are getting absorbed at the surface, that is the core cell mechanism is there, they are attracted to the core. The contaminants are now attracted to the core, and we want to remove this from the water. You place a magnet, permanent magnet there. It will attract them, and with the cell, all these contaminants will be removed from the medium. That is the function of the magnetic nanomaterial over there. So what type of the material it can be coated? As the dendrimers, I have already informed, the dendrimers can be used. You can use the silane, we can use the silver gold cell or the silver cell. In the cell side, obviously the core is the magnetic nanomaterial, and in the cell side we are using different type of the materials like silane, like gold or silver, some polymeric other materials we can use, some acid sewage group containing materials, CONH2, amide linkage may be there. So in this way, polymeric cell can be introduced or dendrimers can be used. So in this way, if the cell is modified, core being the magnetic nanomaterial, and you are adding this as an adsorbent to the contaminated water, and whenever the adsorption process is done, you are going to separate this easily with the help of a magnet. Simple permanent magnet you have to place and you are going to separate this. So in this way, the magnetic nanomaterials can be used for this water water treatment purposes. Sometimes some other polymeric materials can be used also. Some different which are of high molecular weight, they can be used depending on the contaminants that you are want to separate. We can choose the cell material, and polyethylene glycol we can use. We can use the chitosan, which is very important for removal of the dye materials also. Dextrine we can use, polyethylene imine we can use. So the coating polymer, it may vary. You can change the coating polymer. So the design of the magnetic nanomaterial is in your hand. Whatever you want to remove, as per your requirement, you can design the magnetic material. You have to choose a super paramagnetic material as a coat. You coat this in the cell side. You choose the material which will attract the contaminant, or which is the targeted contaminant, and then you just treat water with this material. So these are the different availabilities or different choices for this preparation of the magnetic nanomaterial. And also important, a nanomaterial is there, that is zerovalent iron. Zerovalent iron is also a very good material for this water treatment. And for the zerovalent iron, what is the beauty is that it is iron zero. So whenever the iron zero is there, it is also helping reduction. That is, it is acting as a, it is helping in the reduction of the component that we want to use. As for example, in the tannery waste, you are getting lots of chromium 6, which is very toxic material and you want to remove from the effluent. Now, how we can treat this chromium 6? Chromium 6, if it is coming in contact with iron 0, then what will happen? Chromium 6 will be reduced to the lower oxidation state, that is chromium plus 3. So plus 6 to plus 3 change. That means the toxic form has now been converted to less toxic form or non-toxic form. So in this way, this zero valent iron helps us for reducing the toxicity of some of the effluents. So it is also a very good magnetic nanomaterials that can be used for this purpose. And also, they not only the reduction, some that I mentioned, that iron oxyhydroxides, they can be used for the co-precipitation process. They help in the co-precipitation of coagulation. They are also used for the adsorption. They make the molecules such that the oxidation state is such that they are now getting absorbed with the substrate, and also the reduction that I have mentioned. So this use of the zero valent iron on in the different forms of the iron, that is magnetite and magnetite, they can be used also as a good nanomaterial for the water treatment purposes. This is also the schematic also showing that iron-based these magnetic nanomaterials, they are not only for the adsorption or for the reduction purposes, that is for the conversion of the toxic form metal ions to the non-toxic form. Not only that, but they can also be used for photophantom-like oxidation reaction. That means in case of advanced oxidation principle, they can also help. How they can help? This schematic is showing that if the photophantom-like process, what is there in the advanced oxidation process, we want to produce some active oxygen radical. that will cause the degradation of the persistent organic compounds. Now, by this mechanism, if you can observe this mechanism, it's producing basically the oxygen radicals, the active oxygen radicals. These oxygen radicals, they are what they are doing, they are causing the degradation, but they are responsible for degrading the organic matter to the non-toxic form of this material, or sometimes it is called the mineralization of the organic matter, that is carbon dioxide and hydrogen, the organic matter. If it is degraded, ultimate the objective is to convert this to carbon dioxide and water. So this conversion can be done. This iron oxide, they can help us, they can catalyze this process also. And what is titanium dioxide can also perform the same. But the advantage of this nanomagnetic nanoparticle is that for titanium, its separation is very difficult because it is going to mix up in the medium. And for the separation of the titanium dioxide after the process is done, that is another stage. Another post-processing step is there. We have to remove this, we have to filter this, or we have to membrane separate this. That is catalyst recovery is the problem also in case of advanced oxidation process. But this advanced oxidation process, if the magnetic nanomaterials are incorporated, then the same principle will also act there. That is, after the process is done, you place a permanent magnet over there and it will be totally attracted towards it and you can just remove it. So by using a permanent magnet, you can separate those catalyst systems. So titanium dioxide or zinc oxide or the copper oxide, that is all those semiconductor photocatalysts, then those are obviously the nanophotocatalysts which are used for the asphalt oxidation process. Compared to that, the nanomaterial, that is magnetic nanomaterial, which may also act as a photocatalyst, they are advantageous. Why? Because their separation is very easy. You can easily separate this by after the process is done. No post processing is required. You just place the magnet and it is getting separated. So that's why the magnetic nanomaterial is so important and coming into the picture. And obviously the photocatalyst, we have heard discussed about the TiO2 as a photocatalyst. Photocatalyst, nanomaterial photocatalyst is very, very important. Application is there mostly for the removal of the persistent organic chemicals and as a final polishing state of the water, where sometimes we need to remove the pathogens. Then all this type of the photocatalyst play the role. This is the basic principle of the photocatalyst. The same principle is over there. Our main objective is also the producing of the active oxygen radical, which will cause the organic molecules pollutants to degradation to their, that is mineralization, that is carbon dioxide and hydrogen water production. So now toxic element compounds to the non-toxic degraded product, that conversion can be done by the photooxidation process, that is the advanced oxidation process using the photocatalyst. And those photocatalysts, all those are nanomaterials. Those are TiO2 nanoparticles, zinc oxide, zinc sulfide, cadmium sulfide, all those are there. But as I mentioned that the removal is again a problem from the media. So their removal is a problem. Over this, the magnetic nanomaterial is much better option. But that is also very important, and we can also modify this material. We can incorporate this in the membrane, or we can immobilize those nanomaterials in somehow so that its removal is no longer required. It's already done. It is in contact, the reaction is going on, and it is out. And it is intact in the immobilized state. That can also be designed by incorporating in the membrane or immobilizing on some support. That can also be done in case of the photocatalyst. This is the picture that we have done in our laboratory. That is, in our lab, we have done worked on the pharmaceutical waste, and we are using there. We have just synthesized. We have incorporated that I mentioned, that immobilization of the TiO2, or that is immobilization of the photocatalyst. How this immobilization can be done? They are now trapped in some portion, so that it is not going to get mixed up with the medium. And in this way, the separation is not a problem there. So how can be done? This immobilization was done using this alginate supported TiO2 nanoparticles. The alginate bits are there, which is entrapped in which we have entrapped the TiO2 nanoparticles. And this alginate bits, whenever it is packed over there with the annular photoreactor, the UV lamp is there inside, and we are just allowing the effluent to pass through this reactor, and it is coming in contact with the alginate bits along with the TiO2, and the UV light source is there. Then what is happening? The photocatalytic oxidation is happening, and the water we are collecting, that is free of those organic contaminants, that is pharmaceutical components, are almost, they are reduced. And the observation of our lab is that for ethanol, we have observed about 58% of the reduction is there. For ibuprofen, we have observed about 85%. And for these, this is also a pesticide. For this, we have observed about 80% of the separation. So, and the time requirement is obviously also very low. That is the unique feature of this reactor, the photoreactor. The time is very, very low. Within an hour, we are getting this much of separation. So photocatalyst, nanophotoCatalyst, in this way, it can be used for industrial effluent treatment or for the removal of the persistent organic chemicals or and the pathogens from the water. Now, sensor application of the nanomaterial. Sensor application is also there. Sensor means it's sensing. It's giving you the idea. It's giving you the sense whether the pollutant is there or not. So, these magnetic metal nanoparticles and sometimes the silica nanoparticles, they act in a very good manner. Silica nanoparticles mostly they are used in a biosensor field, and these porous nanosilica materials, what they do, they having a photoluminescence. And if the organic molecule is there or the contaminant is there, then what is going to there? It is now quenched. That is the photoluminescence, what is the property is there, that is now quenched. That means the organic, if its properties has been quenched, that means it's indicating something is there, some organic molecule is there. So in this way, this material, nanomaterials, is detecting the pesticides. It is normally used for the detection of the pesticides. And also some inorganic pollutants, heavy metals, that can be detected in this way. That is primarily basically the fluorescent base. Some colorimetric change is there. Okay. Some nanomaterial is there which is having some color. And if it is going to get bound with some of the other pollutants, it's obviously the fluorescence or its color is going to change. If its color is going to change, then it is obviously an indication that something is there with which they are getting chelated. As for example, the gold nanoparticle. Gold nanoparticle color is something different, and when it is going to get chilled with some other organic material, its color will abruptly change. So that is an indication that this change in the color of the nanomaterial, that is an indication of the presence of the contaminants over there. So using these type of properties, we can use these nanomaterials for the sensor application. And also very important example of this is mainly the gold nanoparticle with IgG, that is immunoglobulin. It can be used as a sensing material for basically for bacterial sensing. It can be used. And using this sensing property, a new term has been introduced, that is sense and shoot. Sense and shoot. Sense you and then shoot. Shoot means you have to feel this. What is that? Here, after we have considered about the silver or the silica material is there, they're changing the color, the luminescence have been changed, and by this way they are indicating that yes, something is there. Now, the same principle is there. We are also observing the emission or over some nanomaterial coated material, that is the zinc oxide is there, and the emission we are observing. Okay, So whenever nothing, no molecule, organic molecule is there, or nothing, no molecules, contaminants are there, so obviously the emissions which we are recorded, that is something different from when some organic molecule is there. So it is going to change. Now, since this material is not only changing the emission, but along with this zinc oxide having the photocatalytic activity also. So this emit light which is falling on the zinc oxide surface, that is also helping its photocatalytic activity. That means organic molecules, they are now degraded. And these organic molecules have been degraded means it is a remedial action. So remedial action is there. It's first sensing, that is no emission, that means something is there. Now it will starting working, and we are providing the UV light such that now photocatalyst will activate. And when the photocatalyst is becoming activated, it is now degrading the organic molecule and converting to the non-toxic materials. That is carbon dioxide unsworn molecules, they are now produced. And obviously, that means what is happening first is sensing, and then it is shooting. That means it's reacting or it's degrading that material. So dual role of this zinc oxide semiconductor film is there, which is acting as a sensor as well as the photocatalyst. So this is also a very good example of the application of the nanomaterial for the water treatment. That is sensor as well as remediation. Sensing and remediation both are coupled. That is by proper choice of the nanomaterial. That means you have lots of options. What is your requirement? Based on that, you have to design this. And in this case, zinc oxide is one of the examples which is helping this process. And this is also biofilm controlling process. I'm not going to this in details also. I've already discussed about this. And why this nanomaterial is antibacterial? If the question comes in mind normally, then why these nanomaterials are normally they are called antibacterial or antimicrobial properties there. That is mainly the reason of the presence of the, that is generation of the active oxygen species, which may cause the cell rupture or it may cause the degradation of the protein matter which is present in the cell. In this way, they are acting as an antimicrobial agent. And this is also a silver modified multi-wall CNT, silver coated as a membrane. I have already discussed that membrane for PES membrane coated with the silver antimicrobial property has been developed. The same way it can be incorporated with the multi-wall CNT also, and we can achieve the absorption as well as the biomolecules or the pathogens removal we can achieve using this type of this combination. And the arsenic removal, for the arsenic removal, this nanomaterials is also very important. Uh, they have a very important role in this arsenic removal. Arsenic 3 and arsenic 5. Normally arsenic 3, and it's normally in these nanomaterials, what is happening, they are not only getting this arsenic residue, they are not, arsenic 3 and arsenic 5, they are not only getting attached with the nanomaterial, but some oxidation and reduction process is also there, and they are changing this from arsenic 3 by is oxidized to arsenic 5. And in this way, the toxicity reduction, it can be done also by this application of the nanomaterial. Normally, the copper oxide and iron oxide, ferric oxide, basically, those nanomaterial combination can achieve this, that is iron toxicity removal purposes, it can be used. And arsenic removal, those materials we can also incorporate in the membrane for this separation. That means in the membrane, when we can incorporate this, their type of material. Here, zirconium 4 has been incorporated in the membrane, has been reported. So when it can be incorporated, then also the same function we can achieve, that is arsenic toxicity can be reduced. And another very smart material, that is the next generation material, the term is coming, that's the nano scavenger. Okay, so nano scavenger is the term, it is almost synonymous like the magnetic nanoparticle. The principle is the similar type. The nano scavengers are also the similar type material. They are magnetically ultra responsive engineered nanomaterials, thus nano scavengers. There is also synthetic antiferromagnetic core layer and the functional capping layer. This similar like the magnetic material that we have used, the nano scavenger. The function is like this. These materials are coated, the similar nature, the materials are coated with or it is in combination with some of the adsorbent, and they are doing their job. Their contaminants are removed, they are getting adsorbed, or sometimes they are remediated, and after that, they are by action of the magnet, they are separated. A very good example of this is the magnetic biochar, because magnetic biochar, everybody knows in biochar, whenever you are working with the adsorption process for contaminants removal, biochar is very important topic nowadays because we all want to prepare the biochar for plastic remediation. That is plastic, that is the polymeric material, the plastic, when it can be easily converted to the biochar. So this biochar is also a good adsorbent. And if you just combine this biochar with the magnetic nanomaterial, then adsorption as well as separation becoming facilitated. That is the advantage of using nano scavengers or the design of the nano scavenger. Now you should ask me why these magnet adsorption material are coupled with the magnetic nanomaterial, because if you are interested about the absorption, you have to use some absorption column. Okay, so column development, the column design is involved there. But the column design is very difficult. Now, it's a laborious process. The column design is there. You have to regenerate the column every time. But if without using any column, the adsorbent can be used as a free mode. But as well as separation is facilitated by simple use of a magnet, then why we are going for the column design? We should use this in a free mode, and there lies the use of the nano scavengers. So using these nano scavengers, the micropollutants, it can be removed also. And magnetic biochar is also capable of removing the microplastic that some of the papers they also have coming that coming in picture, that is they are just observed that the magnetic biochar, they can be used for separation of the microplastic from the water. This is the design of the magnetic that is normally the not only biochar, that is the nano scavenger design is there, and this magnetic in this magnetic that is the scavenger, nano scavenger, this type of functions they are mainly happening. Okay, so the design is obviously in your hand, which type of the polymer you should use or what type of the functional material you should use. That is obviously your choice. As per the requirement, you have to design this, and by this, without using any type of the column preparation or designing of the column, you can just use it in C2. You just add it to the contaminated water, and after the reaction is done, after the separation is done, you just remove it by applying the magnet. This is also the smart wax application of the microplastic removal. And another one more important application is a nano sponge. Mainly it is used for the oil and water separation. The nano sponge is there. Is basically the design of the nano sponge means there is the combination of the hydrophobic material and hydrophilic TiO2 material is there. Hydrophilic nano TiO2 molecules are there. The oil and water mixture, it is now allowed to pass through the sponge. So what will happen? Oil and water is getting filled in this sponge. Now UV light is added. And what is the application of the UV light? It is applied. What is the application utility of this UV light? Whenever the UV exposure is there on the sponge, the TiO2, its nature will change. That is, it will become super hydrophilic material. Now, when this becoming super hydrophilic material, then what will happen? If you just allowing the some air to pass through the sponge, it will try to remove the oil phase because now the super hydrophilic TiO2 and oil phase, they have some repelling action. They will repel each other. So if you are just now allowing the air to pass, then what will happen? Water will be inside the sponge, but oil will be now separated in presence of the UV exposure. After the oil is separated, what is there? All these sponge pores, they are now filled with the water. So oil and water, they are now separated. Now you remove the water, you dry this, and you can regenerate this for multiple time use. So in this way, nano sponge design, it can be used for hydrocarbon separation from the oil phase. That is hydrocarbon and oil phase separation. This nano concept is there. It is nano tube filter, again of this similar type like a nanomaterial, a nanomembrane, and it is mainly used for the removal of the E. coli or bacteria. And this is a design which has been done by Indian Institute of Technology, Madras, Chennai. Here the cartridge system is there, and from this cartridge always the silver nanoparticles, they are coming and they are killing the bacteria. So you are pouring the water, potable water in the tank, and then the silver nanoparticle is coming and they are killing the pathogens. And what the water you are collecting from this tank, that is free of bacteria. So it is again another application of the silver nanomaterial in real life. We have designed this, and probably you all have or used this device or this system also. This is AquaGuard. This is marketed by AquaGuard. AquaGuard on Go that I was talking about. That is, whenever you are going, you are not getting the safe water. You are getting some bad quality water or the potable water. How to make it a drinkable water? That is by application of the using the nano cartridge. The cartridge system is there in the bottle. You put the unsafe water or the potable water in the bottle. The cartridge system is there. You can easily squeeze this bottle, and whenever the water is coming through this cartridge, you are getting the safe water over there. And this is the design basically for the based on the nanomaterial cartridge. The silver nanoparticle is there with some of the metal oxides are there. This cartridge system they have designed, that is the water bottle you can carry everywhere. The cartridge you have to just put, and potable water you can convert it to the drinking water. So you don't have to buy always the water bottles. That is a mineral water bottle. The bottle is in your hand always. So in this way we can also reduce the use of the plastic bottles also. So this is also the real life application of nanotechnology. And this is the chart that's showing the different setups that already been developed based on the nanotechnology. And in India, IIT Madras and Eureka Forbes, they have designed the pesticide filter, and also some of the devices are also there for worldwide. They're developing this type of the system for water treatment, not only for the large scale but in situ, that is for the individual, that is for individual application we are concerned. So individual application, this nanotechnology can be a good solution. And also, these are the charts. I'm not going in detail of all this, but nanomaterials you can use in every aspect. For municipal and urban wastewater treatment, this titoton-based nanomaterial, it can be used. Silver nanomaterials you can use. Similarly, for these pharmaceutical wastewater treatment, we have already discussed that all the organic materials or persistent organic materials or the persistent antibiotics, those can be treated. That means pharmaceutical wastewater treatment, it can be used. Similarly, for the oil wastewater treatment, it can be done. That is oil and water separation, it can be done. And petrochemical industry, it is also having used for separation, for the lowering the COD level, and also removal of this type of the objectionable material from the effluent. And paper industry is also there. This type of use of the nanomaterial is there. So this table says nothing, but just to give you the idea that nanomaterial can be used for each and every effluent treatment. Only we have to think that how we can remove, and only we have to design the material, nanomaterial. And that's way we can solve, or we can design the materials which is desired for the treatment of the effluent and before the discharge to the aquatic body or to the environment, so that the polluting nature of the effluent can be reduced, and in this way we can preserve our water bodies. So these tables are like this. And if you considered about the future, what is the future of the nanotechnology application in water treatment? That is nothing but its incorporation with the its integration with the biotechnology. Nanotechnology is there, and if you just modify this, you can just want to improvise further the nanotechnology, uh, it, uh, nano applications to the water treatment further, then it can be only done with the help of the biotechnology. So integrating this nanotechnology and biotechnology, this is the future of this nanotechnology application in water treatment. You can design the nano bioabsorbent. You can just design the sustainable materials, that is plant-based, some material, nanomaterials you can use for remediation purposes, synthesis of the green nanocomposite materials, nanomaterial based enzymatic biosensors we can design, that is biosensing, the enzyme system is there which is sensing the contaminants, and obviously some microbial nanotechnology, it will help the function of the enzyme in presence of the nanomaterial. So the future of the nanotechnology is nothing but a paradigm shift to the biotechnology, that is integration of the nanotechnology with the biotechnology. We can just further improvise this nanotechnological application for the water treatment. And this is the growth market, obviously, for the nanotechnology, how this fast this market is growing. This is the statistical report is over there. I just got this report from this source. And now the advantage and scopes we have discussed a lot. And one more thing is that after the nanotechnological application, obviously what we are going to accomplish, we are also going to accomplish the zero discharge norms. That is very important in present days. No industry should release anything to the environment. That is the zero discharge norm. Basically, the water, the effluent. Whenever no industries are not allowed to discharge anything. If you want to discharge, properly treat it. Otherwise, you recycle it. Now, nanomaterial is the answer for this. Whenever you are using the nanomaterial, you are recovering the water, and you are recovering pure water from the effluent treatment, effluent, and you can reuse, industries can reuse that water for further application. So zero discharge norms can be accomplished with the help of this nanotechnology. But with the nanotechnology, though we have just discussed a lot about its advantages, but the problem or the limitation is still there, and that is mainly the commercialization of the technology, making it as a sustainable technology. That is a big question, how to make this technology a sustainable one, and obviously the safety issue associated with the nanomaterials. So these are the major concern or major limitations of the application of nanotechnology for industrial applications or for the betterment of the society. And so that much about the theoretical part or the application. Just a brief about our work in our Jadavpur University, what we are doing. That's a brief of that. We are preparing the nanomaterial for photocatalytic reactor. We are synthesizing the nanoparticle modified advanced membrane for treatment of the pharmaceutical wastewater. We are preparing the advanced membrane for the photomembrane reactor. This is photomembrane reactor. And we are synthesizing and characterizing of the novel metal oxide composite nanoadsorbent for arsenic removal. And layered double hydroxide we are synthesizing also for the same purpose, for the good adsorption and for its good absorption property in the nanoscale. And we are preparing the lab scale batch ultrafiltration and nanofiltration unit with the synthesized mixed matrix membrane. So on this topic, research topic, or these are the aspects that we are working on in our lab in Jadavpur University. And these are the achievements from our side. With the ceramic membrane, we have prepared this unit. It is of capacity 100 LPH. It is basically for arsenic removal from the groundwater. We have designed this where it is the ceramic membrane is modified with the nanomaterial. And this design we have just module we have just used, we have already used in some of the severely arsenic contaminated water areas where there is arsenic contaminated water. We have tested, and the observation is that very good removal, that is very good removal of the arsenic removal is there, that is for arsenic 3 and for arsenic 5. That module design with our team, and it is obviously our partner for this designing is Need Innovation. They are helping us in designing this setup. And this is the photomembrane reactor module that we have used, that is we are using in our lab for this photocatalysis process. And this is indigenously designed by us. And this one is the geo-based bottle cap filter. This has already been developed and it is already been distributed to some uh, school. Those are underprivileged, those are NGOs, under NGOs. These are bottle cap filter, which you can fit in the bottle. And if the bottle having the contaminated water, and that can, you just squeeze the bottle and you are getting the safe water. You can consume the safe water. That is geo-based bottle cap filter we have prepared in our lab. And these are major achievements of our lab. And I should like to acknowledge my lab mates and my students and Professor Chiranjeev Bhattacharya, who is in charge of this membrane research lab, for his continuous support for this work, and my students, and for their constant support in developing those of the setups and for the advancement of this nanotechnology application in water treatment, how we can just achieve this. I would like to acknowledge them. Thanks to all of them. And finally, thank you all. Thanks to the organizer for giving me the chance to present here. And I hope my presentation uh, will raise some of the questions, some questions in your mind, not only for this session, but also for future, that how you can use your ideas about the nanomaterials to the help our nature, mother nature. That is the my hope from your side, that I'll feel myself happy if I got some information that with the knowledge of this nanomaterial or with the concept of the nanomaterial, you have developed something new which is in benefit for our nature. So thank you everyone for your kind presence here and for giving me the chance to be present here. Thank you.
Madam, madam, my name is Sohan. Uh, am I audible, madam?
Yes, yes, you are audible.